Welcome to Math 361, Statistical Methods 1. This is the Week 3 online video lecture covering an introduction to conditional probability. The outline for this lecture is we will introduce conditional probability and define it mathematically, and then we'll talk about independent and dependent events. Conditional probability is best introduced via example. So suppose that 3 machines at a factory are used to produce a large quantity of identical parts. The machines have different capacities. Machine A has a large capacity and produces 60% of the parts, while machines B and C produce 30% and 10% of the parts respectively. Historical data indicate that 10% of the parts produced by machine A are defective, compared to 30% for machine B and 40% for machine C. The question we're asked is, if a part is inspected and found to be defective, which machine is most likely to have produced it? Which is least likely? So in reality here, the idea is that we have a tub of identically produced parts, and we pick one up, we find that it's defective, and the question is, which machine most likely has produced it? A, B, or C? Based on our historical data, we see that machines B and C are more prone to producing defective parts. However, machines B and C don't have the capacity that machine A has. So pause the video here and take a guess at which machine is most likely to have produced a defective part. Now, to look how to assign a probability in this scenario, we first have to understand that if we actually pick a part and find it to be defective, at that point, the probabilities we would assign would be 0, 0, and 100 in reality, right? Because that part we pick that's defective was produced by one of the machines and not the others. Now, I don't know precisely which machine it is. So the idea here is that we want to assign probabilities, just like we did before, that obey the rules of probability, but are altered in a reasonable way to accommodate this additional information. So how do we go about doing that? Well, first we should look at what we would do in this problem if we didn't have that additional information. What if we just had a part and we didn't know it was defective? Well, in that case, we'd be looking simply at the capacities of the 3 machines. Machine A produces 60% of the parts. So that's a proportion of the total produced. Now, if I'm going to randomly select a part from the total, that proportion, 60%, then becomes a probability using the classical approach to probability, where all outcomes are considered equally likely. So in the bottom here, or on the bottom here, you see that I assign probability of event A, which will just be machine A producing the part, would be equal to 0.6, 60%. Machine B has a probability of 0.3 of producing the part. And the probability that machine C produces the part is 0.1 or 10%. So without that additional information that the part is defective, the most likely machine to have produced a randomly selected part is machine A, because it produces the most parts, and the least likely to have produced the part we pick is machine C, because it produces the fewest amount of parts. Now, in order to modify these values, 0.6, 0.3, and 0.1, when we get additional information that the part is defective, the easiest way to kind of approach this problem is to look at a hypothetical scenario of, say, 100 parts being produced. So I'll produce or build here a two-way table or a contingency table. Now I see each row is assigned a machine A, machine B, machine C, and I have a couple columns, defective parts, not defective parts, and then a total column on the right. So the numbers in blue on the right, those are just the capacities of the machine. If I assume a hypothetical population of 100 parts, machine A, having produced 60% of them, would have produced 60 parts. Machine B produces 30, machine C produces 10. Now, to determine how many of the parts each machine produces that are defective versus non-defective, I use that historical data. We're told that machine A produces 10% of its parts to be defective. So out of the 60 total, 6 would be defective, leaving 54 to be not defective. Likewise, machine B produces 30% of its parts to be defective. So that's 9 defective, 21 not defective. And machine C has the highest proportion of defective parts at 40%. So of the 10 it's produced, 4 of them would be defective. So the idea here is, how am I going to update or assign new probabilities to take into account our knowledge that we're dealing with a defective part? In essence, we can imagine narrowing down our sample space from the total population of parts, all 100, to only the defective parts. So visually, I am going to limit my attention to just the column of defective parts. I see that there's 19 total defective parts. Now, once again, if I am randomly picking a part, I can use the classical approach to probability. All outcomes are equally likely. And so restricting my sample space in this way to just the defective parts, what would I want to assign as to the probability that machine A produced it? Well, machine A, out of those 19 defective parts, produced 6 of them. So I'll come up with some temporary notation here, P sub D of A. So that's the probability that machine A produced it under the conditions that the part is defective. That's what the subscript D is for. That's going to be 6 out of 19, or approximately 0.316. Likewise, for machine B, its likelihood of producing the part will be 9 out of 19, or 0.474. Finally, the likelihood that C produced the defective part would be 4 out of 19, or 0.211. Note that these 3 probabilities add up to 1. They are an acceptable assignment of probabilities. They obey all the rules of probability set forth in our previous week's lecture. However, they're different than the previous probabilities that we assigned. Originally, without any additional information, we said there's a 60% chance that machine A would have produced the defective part. But now, knowing that the part is defective, we're actually going to lower our assigned probability from 0.6 all the way down to 0.316. Now, why is that? Well, it's because machine A produces the most parts, but it also has the lowest proportion of defective parts, only 10%. Machine B before, which produced 30% of the parts, well, if we know the part is defective, we increase that probability we're going to assign to 0.474. In fact, machine B now is going to be the most likely machine to have produced a part given information that the part is defective. Finally, the probability that C produced the defective part will be 4 over 19, or 0.211. This is a counterintuitive result, which indicates why students have a hard time dealing with conditional probabilities, because machine C produced the largest proportion of defective parts. It was 40% of the parts produced by that machine are defective. However, it has such a small capacity, it produces only 10% of the overall population of parts, that given knowledge that the part is defective, we actually think that machine C would be the least likely machine to have produced it, just because in total machine C produces so few parts. So when we have data presented like this in a two-way table and we're randomly selecting, we have equally likely outcomes, this idea of restricting our attention to some subset of the sample space is the easiest way to approach a conditional probability problem. However, we can't always set up every problem like that, so we'd like to have a formula to apply, in essence, for finding a conditional probability. So the easiest way to motivate what the formula is is to take another look at the same example, go back to this two-way table, but now what I'm going to do is I'll divide every number by 100. So instead of total counts or frequencies in the table, I'll just have proportions in the table. So note now that the lower right-hand corner is 1.00. In this scenario, all these decimal values are proportions, and if I'm randomly selecting a part, so each part is equally likely to have been selected, these proportions then become probabilities. And so I see that probability of machine A producing the part, given information that's defective, that was 0.06 over 0.19, which is 0.316. Well, that 0.06 in the numerator is really the probability of machine A producing the part and it being defective. So that's probability of A intersect D or A and D. And then the denominator, 0.19, that's the probability that the part was defective. So I'm just going to call that event D, and that's the denominator. So the thing to note here, the probability in the denominator is the probability of the given event occurring. So by having knowledge that the part is defective, we're saying the event that a part is defective occurred. That's the given event. Its probability is in the denominator. And in the numerator is a probability of an intersection. So that's how we'll define conditional probability. Let A and B be events such that the probability of A is not equal to 0. That's just so we're not dividing by 0. The conditional probability of B given A, denoted P and then a B vertical bar A. So we read that as the probability of event B given, so that vertical bar translates to given, event A, is defined by the following formula. The probability of B intersect A divided by the probability of event A. It's always the probability of the given event in the denominator. Now note, the notation is kind of weird, that B vertical bar A. It makes it look like we're doing a set operation between two sets, B and A. But it's just a regular probability. We use the vertical bar just to tell us how we're conditioning these numbers. Right? What is the given information? And in the end, these numbers we get are simply probabilities that obey all the rules we set up that probabilities need to follow. Now, because of this formula, you should note that if I reverse the conditioning, instead of saying the probability of B given A, what's the probability of A given B, both of those quantities will have the same numerator, but they'll have different denominators. So in general, switching the order does change the answer. So be very careful about that. Make sure you always read it left to right as first event given second event. And it's always that second one whose probability shows up in the denominator. So let's look at an example. We'll go, before we do that, I should just mention that in class, we'll go over a derivation that shows how this formula is the only formula that will make sense given those rules of probabilities that we set up in the previous lecture. Right? At this point, we haven't made use of any of those rules. We just kind of defined this formula. But I'll show you in class that this is the one and only one formula that makes sense to use. So here's our example again from the 2018 Oregon gubernatorial race. Once again, a telephone poll was conducted between late September and early October by Riley Research Associates for KGW8 and the Oregonian, and they polled 356 likely voters concerning, at the time, the upcoming 2018 Oregon gubernatorial election. The following table shows candidate preference broken down by age group. This is the same table we saw last week in class. Now, given that I have a two-way table or contingency table, I can ask some conditional probability questions. First, if we select a person at random from the sample, what is the probability that the person would vote for Kate Brown given they are younger than 45? All right, pause the video for a moment and see if you can answer that using our approach we covered with the defective parts example. Okay, so since the given information is that the person is younger than 45, will in essence restrict our sample space, at least in our minds, to just the columns corresponding to sample subjects who are younger than 45. So those would be the first two columns. So out of those 34 individuals, 14 of them supported Kate Brown. So the conditional probability of a randomly selected participant supporting Kate Brown, given that they're younger than 45, would be approximately 0.412. Now, once again, we'll check to see what happens now if we switch the conditioning. So now we'll look at the probability that a person is younger than 45 given they would vote for Kate Brown. Pause the video here for a moment and see if you can calculate this new conditional probability. So since the given information now is that the subject supported Kate Brown, we restrict our attention to the row corresponding to sample participants who supported Kate Brown, those 174. And out of those 174, only 14 are younger than 45 years old. So this conditional probability is 14 over 174, or approximately 8%. So note here, by switching the order of the two events, we got a drastically different quantity. So there's another example of showing you that you can't just interchange the order of the two events in that formula. Note, I could also answer both of these questions not using this tabular approach, but by using the straightforward definition of conditional probability, meaning I could have calculated the probability that a subject is younger than 45 given that they would vote for Kate Brown as the probability in the numerator of a subject being younger than 45 and voting for Kate Brown divided by the probability that a subject was going to vote for Kate Brown. So both of them should result in equivalent quantities. Now here's a new question. Does being younger than 45 affect the probability that the person would vote for Kate Brown? Now we want to answer this mathematically using the data we have. We don't want to say, well, of course, people of different ages are going to support the candidates in different proportions. Right? We believe that to be the case, that a certain candidate's not going to have the exact same proportion of support amongst every different age group. But we want to show whether this is the case mathematically or not. So how we can do that is to use conditional probability. Let's compare what the probability a random person in the sample would vote for Kate Brown versus a conditioned probability based on their age. So what I calculated first here is the probability that a randomly selected subject would vote for Kate Brown. Since this is out of everyone, this is 174 out of 356, or approximately 49%. And then I want to compare that with a conditional probability. What's the probability that a randomly selected individual would support Kate Brown given that they're in that under 45 age group? And in that case, using either the definition of conditional probability or restricting ourselves to the appropriate columns or rows, we get the probability to be 0.412. So note that those two numbers are different. So knowledge about an individual's age does affect the probability I want to assign for that person to be voting or supporting Kate Brown. So in this case, the way we call this or say this is that age and candidate preference are dependent on one another. Right? Because that conditional probability is different than the original kind of straightforward unconditioned probability. So these are dependent events. Now, what are independent events? Well, there's a mathematical definition. Two events A and B are independent if and only if the probability of A intersect B, or if you want to call it the probability of A and B, is equal to the product of the two individual probabilities, probability of A times probability of B. Now, this definition is totally unintuitive. The nice thing about this definition works regardless of whether one of those probabilities on the right-hand side are equal to 0. A much more useful version, which is what I used in the previous slide, is at the bottom here. It follows from the definition of conditional probability that if they are independent, then that numerator, that's the probability of B and A, can simply be written as the product of probabilities. And I see that I have a probability of A reducing over a probability of A down to 1, so I get a probability of B out of this formula. So left to right, I see the probability of B given A is simply equal to the probability of B. In other words, knowledge that event A has occurred will not change the probability I assign to event B occurring. That's what we mean by independent. And that's why on this previous problem, because knowledge of the individual's age does affect the probability I want to assign, these would be dependent events. All right, so if you want to check or prove independence, you're always going to be looking at, can I show that the probability of A and B is equal to the product? Or use the bottom equation, is the conditioned probability equal to the unconditioned probability? If that's the case, great. If not, then they are dependent events. Often people take that initial equation on the top as the definition of how to calculate probability of A intersect B. That only works if we know or assume the events are independent. If they're not, then at this point our only approach for calculating the probability of A and B would be to use the general addition rule and rearrange it so that the probability of A and B is on one side of the equal sign. So to finish up here, let's look at one quick example looking at independent events. So we have, after surveying 995 adults, 81.5% of whom were over 30, the National Sleep Foundation reported that 36.8% of all adults snored. 32% of the respondents were snorers over the age of 30. Is snoring independent of age? Explain. Okay, remember, whenever we're asked to look at the independence of two events or the dependence of two events, we always want to use that definition of independence and not just argue from our life experiences. So with a lot of these word problems, the hardest thing is determining what information we're actually given in this problem. So if we look at this, we have the sample size, 995 adults. And then we've told that 81.5% of those adults were over 30. So let's call that the event greater than 30. So the probability of a subject being greater than 30 is 0.815. The National Sleep Foundation then reported that 36.8% of all adults snored. All right, so that's just the probability of a person snoring is 0.368. Right, that's a straight kind of old-fashioned probability. If it instead said that 36.8% of all adults over 30 snored, that would be a conditional probability, right? Because it's talking a number, it's not talking about all the adults in the survey, but only those over 30. So you got to be very careful how you translate these probabilities out of the problem statement and into our symbols. So the next sentence is 32% of the respondents were snorers over the age of 30. So this is the most difficult one to translate. And once again, I look at, is that 32% talking about everyone in the survey or only some subset of the survey? It's not 32% of snorers were over the age of 30, and it's not 32% of those over the age of 30 were snorers. Both of those statements would be conditional probabilities. This is 32% of everyone are both snorers and over the age of 30. So I translate that to be a probability of an intersection of two events, greater than 30 and a snorer, and that's equal to 0.32. So I see here in this case, I happen to have all three quantities I need to make use of the definition of independent events. So what I do is I take the two individual probabilities and multiply them together, 0.815 times 0.368. I see the result is approximately 30%. But that's not equal to 32%, the probability that someone is greater than 30 in age and a snorer. So since those two numbers are not equal, I cannot say they're independent events. Instead, I conclude that they are dependent events. Snoring is dependent on age. Now, you may have wanted to say that without doing any of this math, but the idea here is we got to use the math to prove dependence in this case. That's the end of this lecture. In class, we will go over a few more details about conditional probability, its derivation, some examples, and then look at some more complex problems. And if you're interested, this URL goes to the article written about the governor's race survey, and from that article you can then go look at the actual breakdown of data provided by the survey firm.